Okay, last time we saw the axioms for things like union and intersection and all that. So let's actually try to prove some theorems that have those, operations in them. So let's start with this. Union identity. So S union the empty set is just equal to S, right? So how can we do that? Well, S union the empty set, by definition, that is the set of all X such that X belongs to S or X belongs to the empty set. But X belongs to the empty set. That doesn't make sense because the empty set does not have any members, so that's just simply false. Okay. Well, X belongs to S or false. We know that that's the same as X belongs to S, right? That's one of our axioms, or identity. And the set of all X such that X belongs to S, that's just the set S, right? Because this set contains all of the elements that are in S and nothing else. Okay. So yeah, good. That's QED. Okay. So simple proof. We just got the basically we just open up the definitions and then it takes care of itself. Okay. One thing that I just want to make clear is I snuck in something in this proof, and that is right here, S union the empty set, right? Notice what I didn't do. I didn't say for all S, S union the empty set is equal to S, okay? So I skipped that step. That's because I expect us to kind of know that by now, okay? The other thing that I skipped was when I removed the quantifier for all S, I didn't make it S naught or some symbol. I just left it as S, okay? That's standard practice in mathematics. So in actual mathematics proof, we might have said something like this: let S be a set, okay? And then we would have continued, and standard mathematical proofs are kind of a mixture of English language and math that's just intertwined. And so that's the way that it would be done in a standard mathematical proof. When you do that, then you simply have to remember, okay, that the symbol S does not refer to a variable S, because if it's a variable, I can change it with something else. It's actually a constant at that point, right? Now, I don't know what set it is, right? But it is a constant. I cannot change it. I cannot say, S should be equal to 135. No. It's fixed already. So we just have to remember that even though it might look like a variable, it's actually a constant. That's the usual notation, and I just did that here. I'm probably going to do that more and more as the semester goes on. Okay, so let's move on to our next theorem, okay? Intersection, right? What happens when you intersect something with the empty set? Well, you get back the empty set, right? And here's why. So again, skipping all the quantifiers, I have S intersect empty set and use the definition. So the set of all X such that X belongs to S and X belongs to the empty set. As before, X belongs to the empty set is false, but now I have something and false. Well, that's just false, okay? And the set of all X such that false, that set contains no elements. So it is in fact the empty set, okay? So again, simple, straightforward proof, and we get what we need, okay? So let's do another one. Idempotence, S union S. Okay, what should that be equal to? Well, it's just S. And how do we do it? S union S is the set of all X such that X belongs to S or X belongs to S. This is just the definition. But now I have pure P, which we know is just equal to P, so it's just X belongs to S by the idempotence of or the set of all X such that X belongs to S. That is exactly the set S. So that is our answer. Okay, great. See if there's any other easy ones. Okay, commutativity. S union T is equal to T union S. Okay, well, what's S union T? It's the set of all X such that X belongs to S or X belongs to T. And now I'll use the commutativity of or. It is the set of all X such that X belongs to T or X belongs to S. That's the same as T union S, right? So notice that in this thing, what I have here is definition, right? And definition. And what ties these two together is commutativity of or, right? That's actually been the structure in all of these proofs. We've been using the properties of the logical connectives to kind of show the equivalent properties of the set operations, okay? There's a really close connection between those logical connectives and set operations. All right, let's do another proof about associativity, okay? Let's see if the same pattern holds. So we'll start and say R union S union T. Well, what we have is a union, right? And how do we do union? Well, that's the set of all x that belongs to the first set or that belong to the second set, right? Okay, and the second set is itself a union, so I can open it up. That is, x belongs to S or x belongs to T. Okay, right? Okay, great. But now I can use the associativity of or, right? So I can simply move the parentheses. I have x belongs to R, or x belongs to S, or x belongs to T. And if I look at this part, why, geez, that is just R union S, right? That's what it means for x belongs to R or x belongs to S. That means that x belongs to R union S, okay? And then that is just the definition of the set R union S union T, okay? So again, we use the definitions of sets to kind of break things open so that instead of talking about sets, we're talking about logical properties. And then we use the properties of our logical connectives to kind of create the similar property, associativity in this case, for sets. Okay, so there's lots of proofs that I can do like this. There's lots of proofs I'll ask you to do like this to know that you can kind of move things around as well. Okay, this one's interesting. Oops, let me erase all the things. This one's interesting because it combines union and intersection. Okay, this is distributivity. Okay, but actually you'll find that the proof is almost identical. So we start with R union S intersect T, and then we immediately use our definition of union, okay, to turn this into a statement that has an or. So it's the set of all x such that x belongs to R or x belongs to S intersect T, okay? But what does it mean for x to belong to S intersect T? Well, by definition, that means that x belongs to S and x belongs to T, okay? That's what it means for x to belong to that set, okay, right? But now I'll use the property of logical connectives, the equivalent property, which is the distributivity of or over and so that becomes x belongs to R or x belongs to S and x belongs to R or x belongs to T, okay? Well, each one of these, I can now actually see that, in fact, that is the definition of some set property. So we have here x belongs to R union S, right? And then we'll have x belongs to R union T, right? I could have done that in one step, okay? All right, so now what I have is x belongs to one set and x belongs to the other set. That's just intersection, right? So I have R union S intersect R union T. And that's the end of the proof. Again, same approach as before. Use these set definitions to open things up so that I have statements that are about logical properties, and then use all the properties that we know about our logical connectives to translate those into the equivalent properties of set operations. S is a subset of S union T, no matter what T is, okay? All right, let's try that. This is a subset, right? So how do we prove subset? We say if x belongs to S, then x belongs to the other set, S union T, okay? Again, I skipped over the part where I have the for all quantifiers and where I've removed the for all quantifiers. So all the symbols you're seeing, x, s, t, are actually being treated as constant symbols, not variables, okay? All right, so I need to prove that if x belongs to S union T. Open up the definition, right? And so I have here x belongs to a union. That means that x belongs to S or x belongs... that should be x belongs to T, okay? Well, x belongs to S implies x belongs to S or x belongs to T. That's just P implies P or Q. I don't actually have an axiom for that, but it's clear from propositional reasoning that that's going to work itself out to being equal to true. So again, I just say, well, by propositional logic, basically self-implication, then we're going to get this theorem, okay?